All right, the second type of stoichiometry conversion we're going to talk about is conversions with mass. In most chemistry labs, ours included, quantities are measured in terms of mass. It's really difficult to measure moles directly, so we have to do it indirectly, like we discussed several units ago, and that's by measuring the mass. We can measure the mass of reactants, and we can measure the mass of products. The mass of a substance first needs to be converted to moles in order to relate the two different substances. Remember, for the mole ratio to work, things have to be in moles. In order to do this, we're going to use the molar mass, and it will allow us to convert between mass and moles. Let's highlight this. Must be converted to moles. So there's some sample calculations here in example 4. Calculate the mass of one substance when given the mass of another substance. Same basic idea, except there's a little bit more. So we're using the Haber process again. Go ahead and write in our balanced equation. I prefer to see it on the same page. I find it helpful. So when I look through this, we're going to be finding things like grams of ammonia, here's grams of hydrogen gas, here's grams of nitrogen gas. One of the first things that I would do here is figure out the molar masses of each of these 3 compounds. It's going to make things easier to set up if we've already done the calculations ahead of time. So for these, I wouldn't bother to set up the table. If you're still using the table, that's fine. Maybe try to start doing it without the table for molar masses. But definitely nitrogen, you don't need it, and hydrogen, you don't need it. If you look on your periodic table, the molar mass of nitrogen, one nitrogen, is 14.0. And so the molar mass of N2 is double that, 28.0. And the units are grams per mole. Similar idea with the hydrogen. Molar mass of a hydrogen, 1.01, and with H2, it's double that, 2.02. Again, the units are grams per mole. For NH3, you can use the table if you want, and just to remind you what it looks like. Molar mass. This is how you would do it if you're using the table. And if you're still using the table, that's fine. But like I said, try to get to the point where you don't need the table anymore. I'm going to erase this, and I'll show you how I would put this in my calculator. And it does the same math operations as the table. It just does it without a lot of writing. And I can go straight to the table. Straight to the calculator, excuse me. So here's what I would do. I know that there's one nitrogen, and so that's 14 times 1. And I know that there are 3 hydrogens, and this will give you the same answer. It comes out to 17.0. And so I would recommend starting to do it like this. This is 17.0 grams per mole. So the question here is how many grams of ammonia can be produced from 12.4 grams of hydrogen gas? So what's happening here is we are able to measure the reactant, and we want to know how much product can we expect. This is going to work in a very similar manner to the regular mole-to-mole conversions, with one exception: you have to change from grams to moles. So you're going to start with the mass of the reactant that we know, which is 12.4 grams of hydrogen. Then the first thing you have to do is convert it to moles. And so we want grams on bottom for moles of hydrogen on top. And we already found this number, and it is 2.02 grams for every mole of hydrogen. It's important to note that when you're doing molar masses, it's always grams per 1 mole. This is unrelated to the mole ratio, and it is unrelated to the coefficients in the equation. At this point, we have our units in terms of moles. Remember, we have to convert to moles first, and then we can use the mole ratio. Now that we're in moles, we're ready for the mole ratio. So we are comparing moles of hydrogen with moles of ammonia. This is the mole ratio. This is the step that uses the coefficients from the equation. So for hydrogen, it is 3 moles. That's the coefficient for hydrogen. For ammonia, it's 2 moles. That's your coefficient there. If we were to stop here, this would give you moles of ammonia. But the question is asking us for grams of ammonia. And so we are going to use the molar mass for ammonia. And here's what we want. We want moles of ammonia to cancel. So that's going to go on bottom. We want grams of ammonia in our answer, and it's going to go on top. This is the molar mass step. It is 17.0 grams per 1 mole. Again, grams per mole, per 1 mole. This step has nothing to do with the mole ratio. It has nothing to do with the coefficients of the equation. The coefficients only show up in this single step and nowhere else. So now that we have set up everything, we can go ahead and go to the calculator and find our actual answer. And so what we have is 69.6, and that is grams, specifically grams of ammonia. In the next question, we're looking for product again, but this time we're looking at a different reactant and a different mass for our starting point. 30.2 grams of nitrogen gas. That's our given value. This is where we're going to start. And remember, we have to convert grams to moles before we can do anything else. We've already calculated the molar mass for nitrogen. 28.0 grams will go on bottom, so the grams will cancel. And this is for every 1 mole of nitrogen. The next step is our mole ratio step, where we compare moles of nitrogen with moles of ammonia. This is the step where we need the coefficients. So coefficient for nitrogen is 1. The coefficient for ammonia is 2. And again, if we were to stop here, we have moles of ammonia, but that's hard to measure And so we're going to convert that to grams of ammonia. So for every 1 mole of ammonia, it is 17.0 grams. We'll put this into the calculator, and it comes out to be 36.7 grams of NH3 ammonia. The next one is a little bit different, but they work exactly the same. In this instance, we have 50 grams of ammonia, and so we know how much product is here, or how much product we want, more than likely. And we want to know how much of the ingredients, or how much of the nitrogen gas, is this going to take. First step, use the molar mass to convert grams to moles. 17 grams per 1 mole of ammonia. The next step is our mole ratio step, and we're going to compare moles of ammonia with moles of nitrogen. Looks like a frozen board. And the coefficients here, there are 2 ammonias in the balanced equation, 1 nitrogen in the balanced equation. We don't want our answer to be in moles of nitrogen gas, and so we're going to change it to grams, doing that with the molar mass. 28.0 grams nitrogen on top will give us mass. Moles of nitrogen will cancel. And we're ready to go ahead and put this one into our calculator. It's going to come out to 41.2 grams of N2 nitrogen gas. The next one is, excuse me, the decomposition of water, which we have already balanced. Here it is. Like last time, I'm going to go ahead and calculate the molar masses ahead of time. Now, I don't really want to use the table because we're trying to get to the point where we're beyond that. So what I'm going to do is go straight to my calculator, put parentheses 1.01, that's the molar mass of hydrogen, times 2, which is the subscript, and then plus 16.0 is the molar mass of oxygen, and there's 1 of them. When you put this into your calculator, you'll come up with rounds to 18.0 grams per mole. Hydrogen gas, hydrogen atoms are 1.01 grams per mole. This is H2, so 2.02 grams per mole. Oxygen gas, 16 times 2, 32.0 grams per mole. I like to do these ahead of time so that way when I'm setting up my calculations, I don't have to pause in the middle to figure out a molar mass. I like to just write everything down at once and then go to the calculator. So what mass of water is required to produce 30.2 grams of oxygen gas? Remember the first step. We have to convert it to moles. So there are 32 grams of oxygen in 1 mole of oxygen. Now we're in moles. We are ready for the mole ratio. So we're comparing moles of oxygen with water. We get 2 waters for every 1 oxygen. And then we're ready to change moles of water to grams of water. That's what mass is asking us for, grams. So 1 mole of water we found to be 18.0 grams. Put this in the calculator and it is 34.0 grams of water. Next one, what mass of water, again, grams. What mass of water is required to produce 1.25 grams of hydrogen gas? So we start with our given value, use the molar mass to change it to moles. Once it's in moles, it's the mole ratio. We're comparing hydrogen and water. Both of them have coefficients of 2. And then changing, so 1 mole of water is 18.0 grams. And it comes out to be a mass of 11.1 grams of H2O. Third one, what mass of hydrogen, we're still talking about grams here, can be produced from 1.00 times 10 to the 3rd grams of water? We have a mass here. It's in scientific notation, but other than that, it's going to work the same. Use the molar mass to change it to moles. Then the mole ratio, and we are comparing moles of water with moles of hydrogen. Both have coefficients of 2. And then the molar mass of hydrogen will convert us to grams. And this will give us grams of hydrogen. When we put it in the calculator, we're going to find that it requires 112 grams of hydrogen. And if you want to put that in scientific notation, you could. It's not really necessary. The thing I would say is that this number is 1,000, but this has 3 significant figures. And as long as your answer has 3 significant figures, it's not going to matter that we have it in standard notation instead of in scientific notation.